Okay, I'm going to talk to you about net charge and how to calculate it. I might even throw in a tip or two about PI, isoelectric point. I made this video to try to demystify this. I've noticed a lot of people on forums having trouble with it, and I know that there's the documentation that's out there. It can be kind of confusing. So let's get started. Alright, in doing this, you're going to need a decent command of pH. Alright, so at this point I can imagine you are sick and tired of hearing about pH, but it plays into the calculating the net charge and the isoelectric point. Alright, so what I want you to do is think about the H plus concentration when you think about the pH scale. Alright, we know that 7 and below are acids. What do we want to do if we're an acid is we want to protonate something. So if you stick something in that has potential to gain a H, something in a solution that has an acidic solution, it's going to want to gain their H. Alright, and 8 and above is basic, and it wants to grab an H off of something that has the ability to lose a hydrogen. And that is because it has a higher concentration of OHs, and the OHs want to make water. Okay, so basic wants to deprotonate, acidic wants to protonate, acidic wants to add an H, basic wants to pull an H away. Okay, here's an example. You should be familiar with this guy if you're dealing with amino acids. Okay, the COO here has lost a hydrogen, and we're going to react that with, this is my representation of an acid, and if you throw this guy in there, what do you think is going to happen? Okay, he is going to protonate. He is going to gain that hydrogen. Alright, next we've got this guy. You should be familiar with him. So if we throw him in an acid, and let's look at him, he has gained an extra hydrogen, and if we throw him in an acid, what do you think is going to happen? Nothing. Nothing's going to happen because he's already gained an extra hydrogen, and he has no, he can't go any higher. Okay, so he's just going to stay the same. So what I want you to do is kind of get these four different guys here, just kind of get an understanding of what they can become and what they can't. This guy, if he is thrown into a basic solution, that's going to deprotonate him, because basic, that's 7 and above on the pH scale. If you throw him in there, well, you ain't going to knock this off and just make this an NH2. It's just, nothing's going to happen. If you throw this guy in that basic solution, he's just going to become this, because it's going to knock that plus off and he's going to become that guy. Alright, and if you throw this in the basic one, he's going to knock that H off and he's going to look like this. So in dealing with net charge, you're looking for this positive or this negative here. Okay, alright, so the NH3 positive has a positive 1 charge. The NH2 just has a 0 charge. The COO neg has a negative 1 charge, and this guy, if you get this form, has 0 charge. Alright, so how do we know what these guys want to be at? What pH do they like? Alright, and that's what this scale was. Alright, this is the pKa. This is the pH which this alpha carboxyl group likes to be at. I like to be acidic, or I like the acidic environments. Well, this guy down here, I like the basic environments. Okay, so pretty much this table is probably different than maybe what you have in your textbook, but it's pretty nice because it tells you the 2 different versions of, these are the R groups of different parts of different amino acids, and there's 7 of them. 1, 2, 3, 4, skip that one, 5, 6, 7. You skip these terminals because they're not part of the R groups, but you need to memorize these 2 because they're on every single amino acid. Memorize that this one is an 8 and that one is a 3.1, and I showed you the 4 versions they can become earlier. Now these guys, you'll just might have to just keep when you memorize all your amino acids, you'll understand what the different R groups look like. Okay, so let's take a look here at maybe solving one of these things. Okay, so this guy has a 0, it's neutral. This guy's neutral. It's glycine. It has the neutral R groups on it. They don't have a charge. Okay. All right. So let's react this glycine with an acid. Okay. How do I know it's an acid? Because, well, we'll say it's more acidic. It's less than 7. Okay. So it has a pH of 5. All right. I throw it in there. The first step to solving this net charge on this guy is to go and get the pKa's for the both of the carboxyl and the alpha amino. And they call them the alpha amine and the alpha carboxyl because they're tied to the alpha carbon. Okay. All right. So now we're going to compare these two. All right. This guy likes a pH of 8. All right. But he's being reacted with something of pH of 5. So pH 5 will try to protonate. It's an acid. It's going to protonate this guy. So H3 plus N. He's going to go to an 8. He's going to go to a +1. All right, this guy, he likes acid. This guy's actually basic compared to this guy. So 3.1, a 5 is going to deprotonate this guy because he's more basic, and more basic, even though it wasn't above 7 compared to where he's at, he likes, it is more basic. So 5 will deprotonate this guy, knock that off, and make that a -1. Alright, and I'll show you in the reaction here what happens. And this +1 and this -1, add them together and you get a 0 net charge, which is why glycine has no charge. Okay, and if you can look at this guy, and if you've been studying, you might recognize him. And it's a lysine. Okay, a lysine has a pKa of 10.8. Now we're reacting it with that same pH, so I'm not going to change these two. So we already have the answers for those. We're just going to concentrate on the R group. That's from here down. Okay, lysine's pKa was 10.8. I got it off the little table. All right. So it likes 10.8, and 5 is more acidic, so it's going to try to protonate this guy. So what are we trying to protonate? This, the NH2. All right, so we want to protonate that to an NH3+. Okay, and there it is. So this particular amino acid, lysine, has a +1, +1, -1, gives you a net charge of a +1. These two cancel out, then you just got 1. Alright, so that's why it is one of the positively charged amino acids, lysines. Alright, what's this? Kind of looks like a tire. Okay, and that's what it is. It's tyrosine. Alright, we react that, and I changed the pH to a very basic one. Very, very, very basic. Okay? Tyrosine was already pretty basic, but I even got it more basic. So it's going to try to snatch something off of tyrosine because it's more basic. And what is it trying to snatch? This OH. Alright, you knock that H off that O, and that O just becomes O negative. Alright, and I want to go back to that chart and show you that you can keep referencing back and forth. See, tyrosine, it told us what was going to come off right here. If we react it with a basic solution, it becomes O negative. If we react it with a acidic pH, it's protonated. So this would have been a 0, and that one would have been a -1. So I just want to show you that you can keep referencing back to that. Oh, and then if you, I want to make sure you understand also another example of these guys. So I changed the pH, so this guy has to be reevaluated. So he is more basic than this guy, so he's going to try to pull, he's going to try to deprotonate. So he can't deprotonate any further, so he's just going to say a 0. This guy is going to try to protonate, deprotonate. He's already protonated, so 3.1, a 12 is higher, so it wants to deprotonate. And what does it do? It sure does. It deprotonates to a -1. All right, and then you just add those together, and you got a -2 net charge on tyrosine at a pH of 12. Okay. Next thing we're going to try is a tripeptide. Okay, we're just going to keep adding here. All right, so a pH of 12 again. All right. Now, when you're dealing with peptides, I don't want to go into too much about how to join two amino acids together to create a peptide, but I'll give you a little down and dirty here. What an easy way you can do is, if you've got your N-terminus to the left, and here's my R. It didn't matter if your R is pointing up or pointing down, just make sure they're pointing the same direction. Just take this COOH and this H2N and join them together and just create water. This water molecule, OH2, will break off, and this C wants 4 bonds. He's got 1, 2, 3, 4 when those two join together, and this guy wants 3 bonds. 1, 2, 3. So that's how you join those together in that peptide bond. Just want to show you that real quick. Alright, so the first thing I would do in this one is lay it out. Now that I've got these, I've got an N-terminus amino and an N-terminus carboxyl group, so you add those on because we want to add their numbers into the calculation. Okay, so next I want to throw in my pKa's on top of them. And this is what I'd do on my piece of paper if I was working this problem out. I just draw them out through here, put my pKa's on top. Notice that serine was on here. It has a 0 because it's a 0 net charged amino acid. It doesn't fall into one of my 7. These 4 here fall into, well, these 2 fall into my 7. These are part of my 9. These are on every single one of them. Even this one has these 2, but we're not going to count it. Well, actually, we're counting one of them because it's attached to that one. Don't want to confuse you there. Alright, so the next thing I would do is put my pH over here, okay, because I'm going to react my pH with every single one of these. You can see how this is going. Alright, so I draw myself some little lines across there. And the next thing I do is I say, is 12 is more basic, my solution is more basic, so it's going to deprotonate. Well, can't deprotonate it any further, so it's a 0. Serine was 0, we just bring that down. Lysine, it's more basic, so I'm going to deprotonate the lysine. What does the lysine have up there? Well, you're going to have to look lysine up or memorize it or something, because lysine has an NH3+, and if you deprotonate that, it just becomes an NH2. So you get a 0. It doesn't have a charge. Histidine has that ring, and it has an H on one of the nitrogens that gets knocked off. Okay, and since 12 is more basic, when you knock that off, it's a 0. Now let's take a look at histidine, because that just probably blew your mind. Okay, histidine is right here, and if you react it with a basic solution, it's just 0. Okay, if you put it in an acidic solution, it's going to have a plus, because it's going to put that H up there and change these double bonds in here. Okay, so let's move back down here to carry on. Alright, so the histidine, again, more basic, knocked it off, gave it a 0. Alright, the COOH, alright, that is more basic, so it's wanting to deprotonate this. Now, I know that's probably comparing this to this and this to that. I just say, what is this going to do to that? This is going to deprotonate that. That's the way my pH is going to deprotonate my group that I'm comparing it to. Okay. All right. You saw I added those together. Now we're going to do a polypeptide. And these things, sometimes instructors give them as just the single letter abbreviations. And I'm going to react this with about 3 different pHs. I'm going to show you how to do that. Alright, so I do just like I did before. I spell them all out, and these lines here are because my Microsoft PowerPoint wants to underline things that don't understand. And then I put my terminal groups that's left out there, The reason why we keep putting those out there is because the reason we're doing net charge, we want to know what this whole polypeptide will react with. Well, we got to know the net charge on what's surrounding it. And these are on the outside, of course. We ain't worried about what's on the inside. And these all actually have R groups poking up or poking down, and that's what we're calculating this for. We want to know what the overall net charge is. Okay, so the next thing, just like before. And notice I put those zeros in there because proline, threonine, they all have 0 net charges, okay? Same thing as before, but this is different. We're going to react this with several different pHs. And this gets into the pI stuff here. Alright, we'll take a look here in a second at that. Alright, so we go through and we label everything that got a 0 because we're not worried about those. Okay, after we got our zeros in there, we're going to, and this is the down and dirty version after we're done. Alright, so I'm going to go through each one of them here. So at a pH of 2, this 8 on this amino group wants to be protonated. So let's look at H2N. I want to be protonated. He'd become an H3 plus N. So he gets a +1. Alright, these cysteine has an SH group. Alright, now that's one we haven't really talked about, and it's the only one that has an SH group. Methionine has this S in it, but it's not it's not on the terminal. Alright, so if you react an 8.3, I'm sorry, if you compare these two, this guy wants to protonate that SH. Well, it's already has an H on it, so it's a 0. Alright, the 4.1 here for the glutamic acid, which is an OH. Well, it wants to protonate it, and the H is already there, so it's a 0. And if you want to, what you can keep doing is going back to that table, looking, well, what happens if I protonate it or react it with a more acidic or more basic? Well, you just need to memorize what they look like. So lysine has those NH3 pluses, NH3 plus, and we're going to protonate it. Well, NH3 plus, protonated is a +1. Arginine has an NH3 plus as well. And if you protonate it, well, it stays the same. It stays the same at a +1. Okay. If that was lower, by the way, it would just be a 0, but it's not. Okay, so 3.1, a 2 is lower than that 3.1, so that lower pH is going to protonate this. It's a 0. It's already protonated. So you add those together and you get a 3+. Alright, 7 to 8 is more acidic, so it becomes +1. 7 to 8.3. Cysteine had that H. Well, it's still acidic to it, wants to protonate it, so it's a 0. And why is it a 0? Because SH, it's already got an H on it, it can't hold another one. Alright, glutamic acid. Now this one's different. The glutamic acid has an OH on it, and this wants to deprotonate because it's higher than this. So it's become a -1. It's actually going to become an O negative. Alright, and so I'm not running off and leaving anybody. Glutamic acid right here. See that? Had that H there, knocked it off, and it became, and these bonds here formed and just gave it a negative charge. Okay, so let's talk about it here. So 10.8, it's more acidic. Lysine, NH3 plus. That's what it has, and we want to add something to it. Well, we can't because it's already there. +1. Arginine has that NH3 plus as well. We want to add something to it because it's more acidic. Well, we can. It's already we can't go any higher, so we'll just leave it at a +1. Now the COOH, it likes acid, but it's going to be deprotonated. It's higher. So come across, add those up. These two cancel out. These two cancel out, and you're just left with 1. Alright, next 11. Deprotonates this. Well, it's already deprotonated. It's an H2N. Alright, now it's actually going to pull the H away this time because 11 is higher than this. It's actually going to get that H off this time, of that S. Alright, the glutamic acid of 4.1, it's going to pull one of the H off the OH. Alright, lysine NH3 plus, and it's going to pull one of those hydrogens off that, so it's finally going to be a 0. And arginine doesn't affect that NH3 plus because the 12.5 is still higher. That's wanting to add a H plus to it. It's already there. COOH, well, that is wanting to obviously deprotonate you. There you go, and you just add them up. Now, about the PI, notice this one got at pH 2, this one got +3, pH 7, this one got a 1 + 1, and this one at 11 got a -2. Well, the PI, the definition of PI is the pH at which say a polypeptide is 0. It's that pH where it's neutral. Okay, well, notice it's kind of in between these two, right? +1, -2. So if we come back over here and add in another line in this table, maybe about 8.5, and come across here and got a 0, that would be a good way to find, or that would be one way of finding the isoelectric point. Okay, I hope this helped.